Welcome to lecture 11 of module 3 of the course called Game Theory and Economics. Let me just briefly recapitulate what we have been doing in this course so far. In the last lecture, we have started discussing the theory of auctions in game theory, and so the first auction that we are discussing here is the auction which is known as the second price sealed bid auction. This is just one of the different kinds of auctions that are used. In particular, auctions are used to allocate a kind of precious good or an article among different people. So, there might be different contending parties who will like to have that article, and they have different valuation of that article. What the auctioneer or the person who decides who will get the article does is to that he collects bids from different people and allocates that article to that person who submits the highest bid. In second price sealed bid auction, obviously bids of other people are not known to any particular bidder, and when a particular person is decided to be that person who has submitted the highest bid, he gets the object, but the price that he pays is not equal to the bid that he has submitted. In fact, the price that he pays is the highest bid of the set of people which can be selected if he is taken out of the set of bidders. That is, the price that the person who gets the object pays is the highest bid of the other people besides himself. So, that is what is known as second price sealed bid auction. And so, following will be the payoff here. Here, if B I is greater than B bar, then this person is getting the object, and the price that he pays is B bar, where B bar I is the bid submitted by I, and B bar is the highest bid so this is the case if B I is greater than B bar. However, person I will get the object not only in this case, but also in the case when B I is equal to B bar. So, if B I is equal to B bar and I is less than the indexes of people submitting B bar. So, it is possible that the highest bidder, that is I, has submitted a bid which is same as the bid of the highest bidder if he is taken out of the group. In that case, he will get the object, he may get the object if his index, that is I, is less than the indexes of the other people, which means that he values the object more than the other people. But this is the case, in these cases I will get the object. If I does not get the object, he gets 0. So, we write the payoff is 0 otherwise. Otherwise means if B I is less than B bar, or if B I is equal to B bar, but I is greater than the indexes of the people submitting B bar. So, this is the setting. Now, what will be the set of Nash equilibria in this case, in this particular second price auction? So, there can be several Nash equilibrium in this auction. A particular Nash equilibrium that may seem very natural is this one. The speciality of this Nash equilibrium is very obvious. Each person is submitting the bid which is equal to his or her valuation. In this case, the person 1 will get the object, and the price that he will pay is equal to V2. V2 is the second highest bid here. So, this is his payoff V1 minus V2. For others, payoff is 0. So, this is, I am claiming that this is a Nash equilibrium. Why? Why this is Nash equilibrium is because if player 1 deviates, suppose he deviates and bids something more than V1, which is equal to V1 here. So, if he bids more than V1, then he is still getting the object and his payoff remains the same. So, by bidding more, you are not improving your payoff. If he bids less, then as long as this less bid is more than V2, again his payoff is remaining the same. If he bids less than V2, then he does not get the object and then his payoff becomes 0, which is strictly worse off. So, by changing the bid, player 1 is not better off. So, that is why from player 1's point of view, he is doing the optimal thing. What about other players? If any other player, suppose player 2 bids more than V2, as long as he is bidding less than V1 or equal to V1, he is not getting the object. So, his payoff is remaining 0. He can get the object if he bids more than V1, but if he bids more than V1, if B2 is more than V1, then what is the payoff? It is V2, which is his valuation, minus V1, because in that case the second highest is V1 and which we know is less than 0. Player 1 by deviating and bidding something more than V2 is not better off, he can be strictly worse off. And obviously, by bidding less he does not make any difference to the outcome. So, his payoff remains at 0. And this kind of logic can be extended for other people also, other bidders also. As long as they are bidding less than or equal to V1, their payoff is going to remain at 0. If they bid more than V1, then they can get the object, but the payoff becomes negative. So, this is why this is a Nash equilibrium. So, everybody bidding his or her valuation is a Nash equilibrium, and in this particular Nash equilibrium player 1 is getting the object. But as I just said that the number of Nash equilibria in this game are infinite, there can be infinite number of Nash equilibrium. One particular Nash equilibrium that is of interest is the following. This here in short what is happening is that player 1 is submitting a bid which is equal to V2, player 2 is submitting a bid which is equal to V1, and other players are submitting bids which are less than V2, strictly less than V2. I am claiming that this is a Nash equilibrium. Why this is so? First observe that in this particular configuration of bids, it is player 2's bid which is V1 which is the highest. So, player 2 gets the object, but what is his payoff? It is V2 minus V2, because player 1 has submitted the second highest bid which is in fact V2, and so player 2's payoff from this equilibrium set of actions is 0. What is player 1's payoff? Player 1 is not getting the object, so it is anyway 0, and this is true for other players also. Now, in this case, if player 2 deviates, if player 2 can deviate to from V1, he can deviate to something less. He can deviate to something less, but if the deviation is greater than V2, he is still getting the object, and as long as he is getting the object, his payoff is remaining same at V2 minus V2, that is 0. By bidding more, again he is still getting the object, so the payoff remains same 0. If he bids equal to V2 or less than V2, then what happens? Then he is not getting the object, but even if he is not getting the object, his payoff is remaining 0. So, by deviating, player 2 cannot improve the payoff. So, from player 2's point of view, this is optimal. From player 1's point of view, is this optimal? Player 1 is bidding V2. Now, he can get the object if he bids more than V1, but if he bids more than V1, what happens? Suppose B1 is more than V1, what happens to U1 then? U1 is equal to minus V1. This is the valuation and this is the price that he pays, because player 2 is bidding V1. So, his payoff remains 0 even if he gets the object, and obviously by doing something else, by bidding less than V1, he is not getting the object, and therefore, in fact this is true even if it is equal to V1. So, by bidding less than V1, he is not getting the object, so the payoff remains at 0. Hence, by deviating, the player 1 is not being better off. And this is true for other players also, that is player 3, 4 n. All of them can get the object, but if they get the object, in fact their payoff is going to be negative, because V I minus V 1 will be the payoff, and where I is, and we know this to be a negative thing. So, this set of actions is indeed a Nash equilibrium. Now, this is something which is a little bit curious, because in this Nash equilibrium, what player 2 is doing is bidding more than his valuation. That is, he is bidding V 1, which is greater than his valuation, which is V 2. And it may seem a little unnatural, because a player is risking the case, player is risking a lot in fact, if he is bidding more than the valuation, because if the second highest is also more than the valuation, then he is going to, the first player is going to make a loss. In this equilibrium he is not making a loss, because the second highest is equal to V 2. So, player 2 is just breaking even, but nevertheless it seems a little unlikely that any player will bid more than the valuation, because it becomes a little risky. And this idea is sought to be captured by the following proposition, that in second price auction for any player I, V I weakly dominates all other actions. So, for any player I, if that player bids V I, that is weakly better than bidding anything else. In some case, which means that in some cases this person I will be strictly better off by not bidding anything else, and in some cases he will be indifferent if he bids V 1 compared to any other bid. To exactly show what it, how we can make this proposition is the following. Suppose in this line I am representing B bar. B bar is the highest bid of other players if I take out the player I, and suppose here is V I. Now, if B bar is less than V I, then player 1, player I will get the object. Suppose B bar is here, and he will get the object, and the payoff that he gets is this much, where this value is same as this value. Similarly, if B bar is here, this value is same as this value, and therefore, by connecting all these points, I get the line which represents the payoff of player I. And if B bar is equal to V I, it does not matter whether I gets the object or does not get the object, the payoff remains 0, because even if he gets the object, the price that he pays is equal to V I. So, the net payoff is 0. If B bar is greater than V I, obviously he is not getting the object, so payoff is 0. So, it remains coincided with the axis. So, this is the case of V I is is equal to the person is suppose bidding equal to Vi, then what happens? Suppose the person is not bidding Vi, but less than Vi. Suppose he is bidding Bi dashed. Now, if he is bidding Bi dashed, then if the other player's valuation, other player's highest bid is less than this Bi dashed, then he is getting the object obviously, and the price that he is paying is the difference between Vi and that B dashed. So, this part is same as this part. So, this is 45-degree line once again. But if B bar is greater than B dashed, then this person is not going to get the object. So, at this point it stops here, and after this B bar is greater than Bi dashed, the person is not getting the object, therefore, the payoff is going to coincide with the horizontal axis. Remember, if he had bid equal to V, in these cases he could have got more than what he is getting right now. So, this dotted line is what he could get if he had bid equal to V. What happens if he bids more than V? So, suppose Bi dashed is here. Now, obviously, for all these values of B bar, this is B bar. For all these values of B bar which are less than Vi, this 45-degree line will denote his payoff. Now, if his bid is Bi dashed and B bar is here, then he is getting the object, but he is getting the object and his net payoff in that case is negative. It is Vi minus B bar. So, I have this extension of this 45-degree line here, and this goes all the way until I reach Bi dashed. So, I am basically venturing into the negative territory, which I was not doing here. And that means, by comparing all these three possible cases, the person is at his best, he is doing the optimal thing by bidding only Vi, by not bidding something more. If he bids something more, then in some cases he is worse off. If he bids less, again in some cases he can be foregoing a payoff which he could have earned if he had bid Vi. So, that is the idea. So, in terms of this is Vi, and suppose I am considering this Bi dashed which is less than Vi. If B dashed is here, I could have earned this value by bidding Vi. By bidding Bi dashed, I am not getting that value because this good is going to someone else. That is the idea. So, bidding one's valuation Vi is weakly better than bidding some other valuation. Obviously, if B dashed is B bar is here, it does not matter whether a person is bidding Bi dashed or Vi. In both cases, the person is getting the object and the payoff is this much. So, in some cases the payoff from both the actions, from these two actions are the same, but in some cases Vi is giving the person a better payoff. That is why this is a weakly dominating action. And this is true for any bit which is greater than Vi also. That is why we are saying that Vi weakly dominates all actions, all other actions. Let us do one exercise which is a generalization of this framework. Find all the Nash equilibria of a second price sealed bid auction with two players. We have seen that there are plenty of possibilities of Nash equilibria here, and in particular it is not necessary that person 1 will get the object. It may happen that person 2 gets the object. So, if I take a simpler case of 2 people, not n people, just 2 bidders, then how will the complete set of Nash equilibria look like? So, let us try to solve this problem. So, players, 2 bidders, actions, their bids B1 and B2, non-negative numbers, preferences, each likes to maximize payoff, and Ui, that is the payoff of player I, is Vi minus Bj if Bi is greater than Bj, or Bi is equal to Bj and I is less than j, is equal to 0 if Bi is less than Bj, if your bid is less, or Bi is equal to Bj and I is greater than j. So, this is the payoff function of player I can be 1, I can be 2. We need to find out what is the Nash equilibrium. So, we shall go along the familiar way, we shall try to find out the best response functions and try to see at what areas or what points the best response function of these 2 players are intersecting with each other. So, for player I, Bi, Bj, this is what we need to find out. Remember, what is important here is how different Bj, this small Bj is compared to the valuation of player I. If for player 1, suppose if Bj, that is a bid of player 2, is less than V1, in that case it will be worthwhile for player 1 to outbid his rival. And how does he outbid the rival? He bids either equal to his rival or he bids more than the rival. In both the cases, he is indifferent because he is getting the object and paying the price which is same as B2. So, let us write down the best response function instead of the general case, write down the best response function of player 1. So, this is B1 because the things are not symmetric. That is why we are writing these things, these two best response functions separately, is equal to B1 such that B1 is greater than or equal to B2 if B2 is less than V1. If B2 is equal to V1, then by bidding less, the player 1 is getting 0. By bidding equal or less greater than B2 also, B1 is greater than or equal to 0 if B2 is equal to V1. In this case, by bidding anything, player 1 is getting no payoff, he is getting 0 payoff. So, he can bid anything, there is no maximum to his payoff function. And what happens if B2 is strictly greater than V1? In that case, player 1 will like to lose the object, because if he gets the object, then the price that he will be paying will be more than his valuation, which is not good for him. So, in this case, player 1 will be bidding something strictly less than B2 if B2 is greater than V1, right. So, this is the best response function of player 1. What about the best response function of player 2? Likewise, if B1 is less than V2, then it is worthwhile for player 2 to win the object. So, he will win the object if he bids strictly more than the other people's bid. If B1 is strictly less than V2. If B1 is equal to V2, again player 2 gets nothing. Even if he gets the object, he is getting nothing. If he does not get the object, obviously he is not getting anything. So, in this case, B2 is this. And finally, if B1 is greater than V2, player 2 will like to lose the object. So, in this case, he loses the object by bidding less than B1 or equal to B1. So, this is the complete best response functions of two players. We shall now plot these two best response functions and try to see what are the overlaps. So, this is B1, this is B2. Remember, V1 is greater than V2. This is suppose V2, this is suppose V1. If B2 is less than V1, then player 1 will like to bid more than B2. So, I have this 45-degree line dotted. If B2 is less than B1, player 1 is bidding more than player 2. More than and equal to also. So, this line is included here. If B2 is just equal to V1, any value. So, this is the 45-degree line point, this horizontal line is included. If B2 is greater than V1, B1 should be strictly less than B2. So, this 45-degree line is no longer included. Okay. This is the best response function of player 1. Player 2's best response function, if B1 is less than V2, then B2 is strictly greater than B1. So, this is the V2 point. I have this vertical line here, and all these points will be included. But the points on the 45-degree line will not be included. Secondly, if B2 is equal to B1 is equal to V2, B2 can be of any value. This is the vertical line. And if B1 is greater than V2, B2 is less than equal to B1. So, this line is included. So, we have basically two sets of Nash equilibria here. One is the first set. Let us first describe this set, which is on the northwest. B1 is less than equal to V2 and B2 is greater than equal to V1, and if I describe this set, B1 is greater than equal to V2, B2 is less than equal to V1, and B1 is greater than equal to B2. This line is basically important. I have to consider points only to the right of this line. So, this is a set of Nash equilibrium and this is a set of Nash equilibrium. It is obvious why these are Nash equilibria, just a little bit of discussion is required here. Let us consider this Nash equilibria, this set of Nash equilibria. Here player 1 is bidding something less than or equal to V2, player 2 is bidding either equal to V1 or greater than V1. So, player 2 will get the object in this case, and player 2 will pay a price which is equal to B1. So, if B1 is less than V2, then player 2 will make some positive payoff. And can he deviate and be better off? If he deviates to something less than V1, as long as this less than V1 is greater than V2, he is still getting the object and his payoff is remaining the same. If he bids less than B1, then he loses the object, so his payoff becomes 0. By deviating, he is not being better off. What about player 1? Player 1 is not getting the object. If he wants to get the object, he will have to bid more than B2. But if he bids more than B2, either he gets 0 payoff when B2 is equal to V1, or he gets a negative payoff when B2 is greater than V1 and he outbids player 2. So, by deviating, he is not getting any positive payoff, and so therefore, this is a Nash equilibrium. By the same logic, this other thing is also a Nash equilibrium. Here player 1 is getting the object by bidding more than V2, and player 2 is bidding something less than V1, but at the same time B1 is greater than B2. So, player 1 is getting the object, and he is paying a price which is equal to B2, and B2 we know is less than equal to V1. So, it is either positive or 0, player 1's payoff. By deviating, he can lose to player 2, that is the only thing he can do, but if he loses to player 2, his payoff becomes 0. So, which is not in any case better than what he is getting right now. By the same kind of logic, we can show that player 2 also by deviating cannot be better off. So, these are the complete set of Nash equilibria in case of 2-person second price auction. Let us do one more exercise and then we shall talk about some other sort of auction. This is the exercise. An action affects each of 2 people, so it is a 2-person game. The right to choose the action is sold in a second price auction. That is, the 2 people simultaneously submit bids. The one who submits the higher bid chooses her favorite action and pays to the auctioneer the amount bid by the other person, who pays nothing. For I is equal to 1 or 2, the payoff of person I when the action is A and the person I pays M is UIA minus M. In the game that models this situation, find for each player a bid that weakly dominates all the players' other bids. So, in short, there are 2 players and they are bidding with each other. So, let us call these bids as B1 and B2. Now, whoever is winning this auction, second price auction, is getting to choose an action A, and if he chooses the action A, suppose I wins, then the payoff for I is UIA minus BJ, J is not equal to I. And when I is choosing, so I is choosing A. When I is choosing A, it affects the payoff of the other player also. The other player gets UJA, because this A is entering his utility, his payoff function also, though he is not paying in anything in this case, because he is losing the auction. So, this is the setting, and we have to find out an action for each player a bid that weakly dominates the player's other bids. So, I do not have much time today. Just before we wrap up this lecture, let me introduce another kind of auctions that we shall be discussing in detail in the next lecture, which is called the first price auction. First price sealed bid auction. Now, unlike the second price sealed bid auction, here the story is the following. The people are submitting their bids and the person who is submitting the highest bid is winning the good, is obtaining the good. The price that he is paying here is not the second price, but the price that he himself is quoting. So, the price is equal to the bid that he himself has submitted. So, this is the case, and this is also known as the Dutch auction. The other one that we had discussed before, the second price, is known as the English auction. This is called the Dutch auction because the counterpart, the sequential counterpart of this auction, if this auction is conducted sequentially, it has a real life example, and in Holland this used to be a common practice, that the price that is announced by the auctioneer, it does not start from below, but it starts from above, and then it comes down. So, the auctioneer announces a very high price and asks the bidders whether is there anyone who is ready to pay that price. If he finds no one, then he reduces the price a little bit. As soon as he gets any particular person who is ready to pay that price, that person gets the good and pays that price which he said that he will be ready to pay. So, in this case, you see the story that we had, it is a competition between the two highest bidders, and the highest bidder is going to pay a price which is very close to the price offered by the second highest bidder, does not hold. Here the highest bidder is himself paying the price which he is quoting. Second highest bidder is not material, he does not matter in this particular outcome. So, that is why it is called a Dutch auction. We are going to look into the other aspects of this Dutch auction in the next lecture. Thank you. Why is bidding one's own valuation weakly dominates other bids in the second price sealed bid auction? So, in second price sealed bid auction, price one pays if she gets the object is not equal to BI. Okay. So, because this is the price that I pay, if I get the object is not my bidding, but the second highest, but the price of the highest price of the other players. So, this is why this is called second price sealed bid auction. It might happen that the other price is less than what I have bid. Now, if the price that I am paying is not my bid, then bidding more or less, I am not affecting my payoff. which is Vi minus B bar. B bar is decided by someone else, Vi is given from outside. So, Ui is independent of the bid that I submit. However, by changing Bi, changing my bid, I can change the chance of my getting the object. Okay. So, that is the only difference it makes to the payoff by bidding more or less. Now, there might be some cases, okay, if I consider Bj which is greater than Vi. Now, here Vi, if Vi is equal to Bi, then the player may not get the object compared to the case compared to Bj. So, here is Bj. So, in some cases by bidding Bj I will get the object, but by bidding Vi I will not get the object. But in those cases bidding Bi is strictly worse, because these are the cases where this will happen. If B bar is between Vi and Bj, in these cases by bidding Bj I will get the object, by bidding Vi I will not get the object, but if I get the object I get a negative payoff of this much. So, bidding Vi is always better. In all other cases, suppose B bar is here or B bar is here, it does not make a difference, bidding Vi is same as bidding Bj. So, therefore, Vi is weakly dominating Bj if Bj is greater than Vi. By a similar logic, I can show that Vi weakly dominates Bj if Bj is less than Vi. Briefly describe the first price sealed bid auction. So, here players, n bidders, actions, set of bids which are non-negative numbers, okay, and preferences is given by So, in these two cases where if I bid more than the other player's bid, then I get the object, and the price that I pay is same as my bid, which is Bi, and my payoff is therefore Vi minus Bi. Or it might happen that I am bidding same as the highest bid of other players, but in that case also I can get the object if my index is less than the players who have bid B bar. In that case also I will get the object and get a payoff of this. If these two conditions are not satisfied, then I get 0. That is, two conditions means if my bid is not the highest bid, or my bid is the highest bid, but there is another player whose bid is equal to my bid and whose index is less than my index. In that case also I will lose the object. So, I will get 0.